Air inside the rocket is pressurized to 8 bar. This pressurized air forces the water out of the bottle and generates thrust. The expelled water has momentum downwards, and since momentum is always conserved, the bottle rocket has momentum upwards and travels up. Impulse is the change of momentum of an object. Total impulse can be calculated by integrating the force multiplied by the time. Force in this instance is the thrust acting on the rocket. The maximum instantaneous impulse in this simulation is shown to be 16.8 Newton seconds. Using the simulation, we can see the effect of changing water fraction on impulse. This helps us in determining which water fraction is ideal. As always, this is just a simulation and is likely to deviate from the real world scenario.
We decided for this design to have fins in the bottom, as this puts centre pressure below the centre of mass. As a result, this will increase stability in the perpendicular axis and it will return to equilibrium much faster. In this design, there are fins in the middle. We went against this to keep the centre of pressure low. Fins in the middle also has lower directional stability as shown in Unity. Directional stability is the stability around the perpendicular axis of the rocket.
As being demonstrated, Unity was used to test the relation of parachute diameter to terminal velocity. A larger parachute creates a greater drag force, slowing the rocket by a greater amount, which is what we're aiming for. However, a larger parachute takes longer to deploy, which is also shown in this Unity simulation. We used Unity to collect data about the terminal velocity of each parachute diameter and created a graph. This graph has a linear relation till 0.5 meters, where the increase in benefit decreases. So we decided to use a diameter of 0.5 meters for our parachute.
To build a good rocket, we needed to have a good design, and we had to have a good build quality. So we decided to use tape as a protection for our bottle as we applied hot glue. We also decided that our nose cone should be manufactured with 3D printing to increase its durability, therefore protecting our payload better. Our parachute would be 0.5 meters in diameter to ensure a good amount of drag force and not weigh the rocket down too much. Finally, we decided that the fins should be at the back for greater stability. We used a fizzy drink bottle, which is made from a more durable plastic than what a normal drink bottle would have been made from, which will ensure us that it won't explode while we pressurize it to 8 bar. As most people know, weather in the northern UK is not always perfect. It can rain any time, causing deterioration on components. Also, powerful winds can sway the rocket off its trajectory, and conditions affecting air density, such as mist, can lower the efficiency of our parachute.
Over the first couple of weeks, we've used CAD software such as SolidWorks to design and experiment fins and nose cones. Through many iterations and health and safety considerations, we have modelled our nose cones of a rounded tip for obvious safety reasons, but also the fact that in simulation it was shown to reach a greater height. Similarly, with the fin design, we have tested different sizes in Unity and designed sketches in SolidWorks so they could be laser cut. In the end, we chose a triangular fin and used light black foam instead of a plastic foam hybrid, as it is lighter, safer and less sturdy to avoid the bottle from bending.